down, I think.
I think so, yes.
Mm. Okay, we're on record now. We've got a few more minutes, so we'll just wait around and let people join.
Yep. Hi, Matt.
Hi, James. Hi, Andrew.
Hi there, Matt.
How you doing?
Good.
Thank you.
Mm.
I'm in Vienna right now, so the afternoon scheduled talk works quite well.
Oh, perfect. That's great. Hello, Goyen.
Hi, how are you, James?
Good, thank you. How are you doing?
Good, thanks. So are you still in your office or?
Yes, yeah. I'm in my office. Yeah.
I see. I saw you going to somehow a conference overseas, or?
No, not this week. But...
I see. But good to have you for a series of talks.
Yeah, it's a real pleasure to do them. So
Yeah, I look forward to the talks. All right, so I'll stop my videos.
Hey, everyone.
Hi, Marika.
Hi, Marika.
Where are you joining us from today?
Today from Germany, nearby Frankfurt.
Oh, excellent.
We'll wait just one more minute and then I'll do the introductions. All right, we might get started. So it's my pleasure today to be the chair of the first session here and to introduce James. So for those of you who don't know about MoCaO, which is the organisation that's putting on these lectures, well, the MoCaO is the Mathematics for Computation Optimisation, which is a special interest group of the Australian Mathematical Society. Our special interest group is dedicated to promoting the activity in the field of computation optimisation in the broadest sense. The MoCaO lecture series is an annual event that we began in 2022 with a series of talks on data science given by Steve Wright from the University of Wisconsin-Madison. We continued the series this year in 2023 with our MoCaO lecturer, Dr. James Saunderson from Monash University, who will talk on polynomial optimisation, an area that has attracted a lot of activity in the last 2 decades. In these lectures, James will introduce the basic ideas behind the techniques and discuss some of the more recent developments. These lectures are designed to be accessible to novices of the field, such as PhD students, postdocs, and inquisitive academics. James Saunderson is a lecturer and an ARC DECRA Fellow in the Department of Electrical and Computing Systems Engineering at Monash University. He received his PhD in electrical engineering and computing science from MIT in 2015 and held a postdoctoral position at Caltech and the University of Washington before joining Monash. So I welcome James and I thank him very much for being our MoCaO lecturer for 2023. And over to you, James.
Wonderful. Thanks very much, Andrew. And thank you very much to the MoCaO executive for inviting me to give some of these lectures this week. We also have two fantastic other lecturers who will be giving the talks on Thursday and Friday. And I'll say a bit about that in a second. So let's jump right in. And I think before I do, the only thing I want to say is that I do hope, I believe we have some seasoned experts in the audience. So I apologize, or maybe not, to you if some of this stuff is very well known to you. I hope there's something in there that's new, but I'm really focused on, or trying to focus on, those for whom this is kind of pretty fresh and you haven't seen much about this before. So that's where I'm aiming. Okay, so let's get started. So the topic of these talks is nominally polynomial optimization. And I want to start by saying maybe something controversial or not. I'm not sure about optimization. So what do I mean when I think about optimization, mathematical optimization? I think of this as having two pieces. One I would call maybe improvement. All right, so that's like I've got some cost function, maybe it's kind of crazy. I start somewhere, I do something to get to a better feasible point that has a better cost, and I improve my feasible point, and eventually perhaps I get stuck somewhere, I can't see how to improve. There's lots and lots of different algorithms and ideas and methods associated with doing this, often very powerful and very successful. One of the challenges is that it's pretty hard to know whether I'm kind of, how well I've done. When I get stuck, it's pretty hard to know how well I've done in general. Right, but often it's kind of, we've got good techniques to do this. I think the other side of optimization, and one where perhaps, the techniques are in some ways, although there's plenty, they're a little bit more limited, it's a little bit harder to see how to get started, is what I might call certification. All right, so how do I certify, for example, in this picture, a global lower bound on the optimal value of this function, right? So I can't do this by plugging in feasible points because they all give me upper bounds. So I need some other method to produce global lower bounds, right? And so the focus of, certainly this part of these lectures, and I really think that most of the week, is really on trying to understand tools and techniques for doing certification rather than necessarily for improvement. Okay. Right. So in these lectures, we're going to talk about polynomial optimization as a starting point. So what do I mean by polynomial optimization problems? Okay, so simply I mean an optimization problem with many variables. We'll typically have n variables, right, where the aim is to minimize some multivariate polynomial, p, subject to multivariate polynomial inequality and equality constraints. So in particular, I'm thinking about polynomials in these talks with real coefficients, and I'm thinking about plugging in real variables. Okay, so that inequalities make sense, and so that optimization makes sense. Okay, this is a very expressive class of optimization problems. In general, of course, it should be very difficult to solve problems like this. And what we're going to do is develop a toolkit, of a systematic toolkit to try to certify lower bounds. So these are minimization problems, but to try to certify lower bounds on these, on the optimal value of polynomial optimization problems. All right, and you could think about this as a toolkit that would complement any tools you've got to plug in feasible points and search among feasible points for good points. Right, so you might have tools to do that. A certification of a lower bound will allow you to complement that by saying, hey, yeah, you found a good feasible point. You probably should stop trying, or maybe not. Maybe oh, you're potentially really far from optimality. Maybe you need to keep looking. Okay. So this is what I'm going to mean by polynomial optimization. And that's pretty concrete. On the next slide, I want to go to another sort of optimization problem that involves polynomials, okay, but looks a bit different. So So let's see. So this is what I'm going to call optimization over non-negative polynomials. All right. And this is going to look a little bit crazy at first if you haven't seen anything like this before. That's okay. We're going to come back to this, kind of see where this comes from sort of more slowly later in the talks. But I just want to put it out there very briefly. Okay, so now we're kind of going to flip things around. Before our fixed data of the problem were a bunch of polynomials describing the objective function and the constraints. So now we're going to think about polynomials as being decision variables. And to be really concrete, we're going to think about maybe the decision variables as really being the coefficients of polynomials. Okay, so we're going to think about the coefficients of polynomials as decision variables. And we're going to be trying to minimize the cost function of those coefficients subject to some constraints. All right, and even we're going to limit ourselves to linear objective functions and basically affine constraints, so kind of linear equations. And the one interesting constraint is that we're going to require that these polynomial decision variables have some non-negativity properties. So in this example, what I've done right here, we're going to ask for it to be a globally non-negative polynomial. Okay, so this is some other kind of optimization problem involving polynomials. We're going to see that it's closely connected to the polynomial optimization problem on the previous slide, but it will be helpful for us to consider this kind of turns out to be sort of bigger class of optimization problems. Okay, I just want to say that, we can extend this basic model to have multiple decision variables where each one is a polynomial, and we may want to relax this instead of having our non-negativity constraint being global, to have it being non-negative over some feasible region, over some smaller region. Okay. So just as we're interested in what we can model and how we can bound the optimal value of polynomial optimization problems, we're interested in similar questions for this other kind of optimization problem involving polynomials, where the decision variables are polynomials and the constraints involve the non-negativity of polynomials. All right, so that's kind of the warm-up. These are going to be the main players as we go forward in the lectures this week. All right, so what are the lectures going to be about, roughly? Okay, so we're going to be looking at, as I said, systematic methods to find lower bounds on the minimum of polynomial optimization problems. And to do that, we're going to connect to this class of optimization problems over non-negative polynomials. This is going to be basically the confluence of sort of two streams of ideas. One is ways to certify the non-negativity of polynomials using kind of concrete non-negativity revealing descriptions called sums of squares that we'll see later. So that's one piece of the puzzle, is connecting non-negativity to sums of squares. And then the other piece of the puzzle is going to be to recognize that problems involving constraints where polynomials are sums of squares, whatever that means, are going to be connected to certain convex optimization problems for which we have, good algorithms and that are quite well understood, called semi-definite programs. Again, I'll introduce all these terms later on, so you know what they are if you haven't seen them before. Okay. So the first three lectures, in fact, the first two lectures are going to be really about introducing the basic tools. So they're going to be somewhat tutorial style. Okay, so today we're going to introduce a bit more about polynomial optimization problems, more about an abstraction called conic optimization, and then kind of this idea of certification of non-negativity via sums of squares. Okay, so that's going to be today. Tomorrow's talk, we're going to try to build these ingredients together to give a kind of toolkit to attack polynomial optimization problems and decision problems, so things where there's no objective function, to attack these using this semi-definite programming tool. Okay, so that's going to be kind of the theme of tomorrow's lecture, is really to build a toolkit and understand sort of why it works, or a little bit about why it makes some sense. And then in the third lecture, we'll look at some more examples. There'll be examples peppered throughout, but some more examples. And in particular, I'll try to zoom out a little bit and give a flavor of sort of some recent research directions in this area. Okay, that's going to be the first three lectures. And then I'm really pleased to have two fantastic lecturers giving the last two talks. So we're going to have Georgina Hall from INSEAD giving the talk on Thursday. And she'll be sort of talking about, in some sense, some of the computational limitations of the toolkit that I'll be talking about in the first few lectures. Okay, and some recent ideas about how to overcome some of those limitations and make these methods more scalable. And then lecture 5, Marijke Dressler, who's online and can tell me if I'm saying the wrong thing here. So she's at UNSW. Well, not right now at UNSW, but based at UNSW nominally. So Marijke is going to talk about kind of another way to certify non-negativity, which, as I said, is kind of a core idea here. An alternative to sums of squares to do this. And this connects to other kinds of convex optimization problems rather than semi-definite programs. Okay, and this has lots of other interesting benefits and lots of other ideas there. So that's the basic outline for the book. Okay, so without further ado, let's get going. And I want to get going with a number of examples to start off with, to sort of whet your appetite to see what we can model with this notion of a polynomial optimization problem. And the reality is, you can probably imagine that if you're allowed to make constraints that are multivariate polynomials and objective functions that are multivariate polynomials, I mean, you can approximate pretty much any problem, any reasonable problem, because polynomials are already very expressive. So, of course, a huge range of problems fall into this class. I just want to mention a few concrete examples in the coming slides that are fairly simple to absorb. And these come from areas such as, they'll be coming kind of from areas like control theory, from partitioning problems in graphs, so kind of clustering type problems. There'll be some other graph problems that are closely related to packing problems, as we see in the picture here. And one that I'm not going to talk about today, but I hope to get back to later in the week, is a problem coming from quantum information theory. So very different areas that sort of give rise to natural, nice structured polynomial optimization problems. Right, so let's look at a really concrete example, just to give you a sense that this can definitely encode hard, interesting problems. All right, so take your favorite hard combinatorial optimization problem. So mine is the max cut problem. So what's the max cut problem? The input is a graph with vertices and edges, such as in the top right. And in the max cut problem, we're trying to maximize over a subset of the vertices. Okay, so that's our decision variable. And what are we trying to maximize? We're trying to maximize the number of edges that cross between our special subset and the complement of our subset. Okay, so in this picture, my subset is the red set, the complement is the black set of vertices, and the blue edges are the cut that go between them. Okay, in this case, the cut has size 6. All right, so this turns out to be a hard problem, but this kind of partitioning problem in graphs, I mean, not exactly this formulation, but is very closely related to many kinds of different clustering and community detection kind of problems in machine learning and in network analysis. So it's kind of a prototype for a whole bunch of graph problems. Okay, so, but I said this is about polynomial optimization, and this looks far from having any polynomials, right? I mean, this is kind of a combinatorial problem. Where are the polynomials? So the first thing I want to say, because it blew my mind the first time I saw it, is that with polynomial constraints, in particular with quadratic constraints, okay, you can model binary variables, right? So for example, if you want to use plus minus 1 variables, you can use the constraint x squared equals 1. Or if you want to use 0, 1 valued variables, you can use the constraint x squared equals x. Okay, and so with this in mind, I'm going to assign a plus or a minus 1 to every vertex. Okay, and then I'm going to try to optimize an objective function. And if you look carefully at this function, it's going to take value 0 if I and j are in the same group. Okay, if they're both assigned plus 1 or both assigned minus 1. And the whole thing is going to take value 1 if they're both assigned, if they're assigned in different parts of the partition. Okay, so you get a quadratic objective function, quadratic constraints, and you can model this, combinatorial optimization problem. Right, so you can already see that polynomial optimization, even in its most basic sort of formulation with quadratic costs and quadratic constraints, second most basic, I guess, can model hard things. Okay, I want to move on to one more problem. I mean, I'm going to apologize, but again, not apologize for it being another kind of combinatorial looking problem. Okay, but I want to talk about it for a reason. So this is the maximum clique problem. Again, my input is a graph with vertices and edges, and I'm again trying to find the subset of the vertices. I want that subset to form a clique, so to be completely connected. So every pair of vertices in that set is connected by an edge. I want to maximize, say, the number of vertices in the clique. Okay. So if we took the same kind of approaches on the previous slide, we could write down, you would write down fairly quickly a polynomial optimization formulation of this. We'll use, say, 0, 1 variables. Okay, 1 for each vertex, some sort of constraint that encodes being a clique. So being the indicator function of a clique. And then we're going to try to maximize the size of this thing. Okay. All right. But the reason I wanted to talk about this is that, this polynomial optimization, language is very flexible, and there's often very many different formulations of the same problem. I just want to show you one that's kind of, again, crazy and quite different, but also kind of models this maximum clique problem. All right, so what is it? So it turns out that after manipulating a result from the 60s that doesn't quite look like this, you can show that this maximum clique number, or at least some transformation of it that's easy to undo, okay, is actually given by maximizing a quartic polynomial, so a degree 4 polynomial, okay, over the unit sphere. All right, so sort of, again, a combinatorial optimization problem, but now our variables are really continuous, and sort of somehow by what seems like magic at the moment, the maximizers of this particular quadratic are in fact related to the maximum cliques in this graph. Okay, so one of the things I want to say is that there can be many different formulations of a problem, and it's a real art, to understand which formulations work better. I think this is a theme generally in optimization, but that's very much a theme also in these polynomial optimization problems. The last thing I want to say is that there is a connection. This problem connects to a bunch of other things. One thing is like densest packing problems. So if you want to say pack pentagons as densely as possible, like in this picture, how can you do that? And you can actually model that problem as finding the maximum clique in the complement of a graph. It's a graph with infinitely many vertices, but a graph nonetheless, that's somehow related to this packing problem. Okay, so kind of a packing graph. And people really still find ways to use polynomial optimization techniques, particularly combined with symmetry ideas, to attack those problems. Okay, the other place, similarly, these things have come up is in understanding bounds on error correction codes in communications and information theory. All right, so somehow this fundamental problem shows up in different guises in a bunch of different places. Okay. Another problem I want to show you, this time a more naturally continuous problem, and it's kind of a generic problem, is to look at essentially the distance to a variety, so to a set defined by polynomial equations. And I want you to think about the set of points x that satisfy these polynomial equations as kind of an unsafe set, so a bad set that you'd like to stay away from. So maybe, like, to give a concrete example here, suppose I estimate a matrix from data, okay, and I want to solve a linear equation with this matrix that I've estimated from data. Okay, I want to sort of understand, and maybe I have more uncertainty in certain entries of the matrix than in other entries of the matrix. I want to understand how far is this matrix from being kind of this linear system from being ill-posed? So how far is my matrix from being singular? And of course, we understand how to do that when we allow arbitrary perturbations of the matrix via the SVD and so on. But if I only allow certain perturbations in my matrix, so I've got uncertainty in certain entries but not in others, how do I bound this distance to singularity? Okay, so this is kind of a toy problem, just so it's easy to write in the slides, but it's a kind of toy instance of a more general type of problem that comes up, for example, in dynamical systems and control. So in robust control, one often wants to understand, again, I've got a nominal model of a dynamical system that I've designed a controller to make it stable, whatever this means, if you know what it means. But you want to know, like, how much can I perturb my model if I've got uncertainty in some parameters and be sure that the thing is still stable. Okay, so unstable models would be the bad set. And I want to understand the distance between my nominal model under some perturbations and a kind of dangerous model, an unsafe model, which here might be an unstable one. Okay, but so in this toy model, okay, we could be given a matrix, and we want to understand, how much two-norm perturbation can I have on the diagonal and remain non-singular? And so this I could pose as a polynomial optimization problem. Okay, I want to minimize the distance between x and my nominal point. In these coordinates, my nominal point in the x variables is 0. That's no perturbation. Okay, and I want to sort of understand the minimum value, the minimum distance to the bad set. Okay. One of the reasons I want to bring up an example like this is that this is a situation where, okay, yeah, I'd be very happy if I could solve this problem exactly. Okay. All right, but I'd also be quite happy if I could find a lower bound. All right. So if I said, okay, if I said that, you know, I don't know the exact value of this minimum. Okay. I don't know the exact value of the distance to the variety, but I know that the distance to the variety is at least 2. Okay. Then I know that any perturbations by 2 are safe. Maybe I could make bigger safe perturbations, but this would tell me that I know for sure that any perturbations of size 2 are safe. Okay, so this kind of scenario where certification is really important. So be able to know, I don't maybe care as much about exactly solving the problem, but I do care about having kind of global bounds on the distance to my bad region. Okay. So those are just a few kind of somewhat random, but interesting for different reasons, examples of polynomial optimization problems that we will be able to kind of tackle with the tools that come up in this lecture series. Okay. I want to briefly say something about what we can do with this other class of problems that I introduced earlier that I called optimization over non-negative polynomials. So this is where we flip things around. We had a polynomial as the decision variable, and the constraint was the non-negativity of that polynomial, possibly over some region. Okay. And so the first thing is, okay, what can we model with this class? Well, turns out we can model polynomial optimization problems with this class. And this is kind of on this slide a really, really, really key idea for what we're going to do in these lectures and how we're going to think about polynomial optimization problems. So I'm going to start with the unconstrained setting. Okay, so my problem initially is an optimization problem where the decision variable is, you know, a point in Rn. And instead of solving that problem, I want to think about producing global lower bounds on my polynomial. Okay, so what does it mean for the constant function gamma to be a global lower bound on my polynomial? Well, that means that my polynomial minus gamma is a globally non-negative polynomial. Okay, so this is a globally non-negative polynomial. And what do I want to do? I want to maximize this lower bound. I want to find the biggest lower bound that's below my polynomial. Okay, and if I can do that, I will have solved the original, I will find the optimal value of the original problem. Okay, so this is kind of a key transformation. But the other thing I want to say is that sort of here I could think about the decision variable as being a degree 0 polynomial, gamma is the number. The objective function is linear in gamma. This constraint is somehow, you know, affine in gamma. So P is a constant, gamma is my variable. And the non-trivial interesting piece of the constraint is saying that some polynomial is globally non-negative. Okay, so it's kind of in this form that I saw before, at least for unconstrained polynomial optimization. All right. So what about constraints? Well, okay, we can play the same game, of course. If I want to optimize over some constraint set, suppose it's perhaps defined by polynomial inequalities and polynomial equations, right? For example. So again, potentially very complicated constraint sets. Formally, we can do exactly the same thing. We can say, well, that's equivalent to maximizing our lower bound, but now I only require the non-negativity of this polynomial over the constraint set. And so somehow if we could characterize, or if we could give a good description or a good approximate description of polynomials that are non-negative over a set, or polynomials that are globally non-negative, we could attack these polynomial optimization problems. Okay. So that's one sort of application scenario for this situation of solving optimization problems where the variables are polynomials and the constraints are the non-negativity of polynomials. I want to give you another kind of application scenario where where it's less about optimization and kind of goes a bit beyond sort of the optimization sort of viewpoint we've been taking. Right. So another scenario where this kind of story comes up is in trying to prove the stability of dynamical systems. And in particular, we'll talk about ones that are defined by polynomials. Okay, so I could have, so what do I mean by this notation? I mean that I've got a vector variable x, say in this picture, x1, x2, and its derivative with respect to time is a polynomial function of the position you are in the state space. Okay, so these arrows, for example, in this example down here, the example is coming from a nonlinear model of a jet engine, it turns out. These arrows are telling you the direction of the vector field, and you can see the flow lines of the differential equation kind of following these arrows. Okay, so you can see that this, I mean, at least from the picture, it looks like all of the trajectories of this picture are converging to this point in the middle, and this turns out to be the origin. Okay, but how can we prove this? I mean, so how can I prove this, for example, this notion of what's called global asymptotic stability, which means that if I start at any initial point in the state space, and I, evolve the dynamical system, that the trajectories will converge to the origin. Right, so it's kind of just like, proving a global bound on a function, kind of naively, I have to plug in all the points and see what the smallest one is. The same here, kind of a naive approach would be to say, okay, I need to start at a whole bunch of initial conditions and simulate the differential equation and sort of see that I converge to zero, but this is no proof, right? So how can we come up with a proof of this? There's a very nice idea that's been around a long time now, is that we could sort of prove stability if we can find a function, a kind of auxiliary function that proves stability for us. And so what does it want to do? Well, it wants to be a positive function, except maybe vanishing at the point where everyone wants to converge. All right. And what we wanted to do is we wanted to decrease along trajectories of the system. All right. So wherever I start, it's got some value. And then as the differential equation evolves, I want to make sure that my function decreases. All right. So think of it like an energy-like function that's kind of decreasing over time. Right. So if we had such a function, we would get a proof of stability of this dynamical system. All right. And so this, again, so far, okay, where's the connection to this optimization over polynomials? Well, one way to approach this is to restrict our search to polynomial functions. That's a restriction, okay? But this is an optimist's game. If you find a good function that proves what you want to prove, you're happy. If you don't, well, you were just in the same place you were before, you didn't know. Okay, so we're going to restrict ourselves to polynomials. Okay, and it turns out that we can prove stability by finding a polynomial that satisfies sort of our same positivity conditions, which are exactly the kind of positivity conditions or similar to the positivity conditions we've seen earlier, plus another condition. And if you just go and do the chain rule, okay, this is really the chain rule, you'll see that decreasing along trajectories, okay, once you do the chain rule and you substitute that x dot equals f of x, is the same as a linear expression, okay? So this is something that's linear in V, okay, because f is fixed, that's data of the problem. So some polynomial that's linear in V being, globally non-positive, okay? So this is kind of, again, a connection between a question that looks quite different from optimization, but a connection to one of these optimization problems over non-negative polynomials. The only thing here is that we don't have an objective function, right? This is just a feasibility question over non-negative polynomials, but it has the same characteristics of linear constraints, okay? And, one or two, in this case, interesting constraints, and the interesting constraints are essentially global non-negativity type constraints on polynomials, okay? And again, the decision variable here is a polynomial. All right. So that's kind of some smattering of motivating examples to kind of keep in mind as we go through these talks. Now what I want to do in the next section of this talk is start talking about tools, okay? And so the first collection of tools I want to talk about come under the umbrella of a thing that I'm going to call conic programming. Right. So this is going to be a way to think about a whole lot of different convex optimization problems. All right, to put them in a unified framework in a way that will take us from hopefully something quite familiar on the next slide to our kind of crazy optimization problems over polynomials a few slides later, and we'll see them in kind of hopefully one consistent light. Okay, so where are we going to start? We're going to start with linear programming. All right, so linear programming is hopefully familiar to many, if not everybody. At least you've seen this, but if not, you're going to learn what linear programming is right now. So linear programs are a family of optimization problems. They involve a linear objective function, a decision variable x, which is a vector in, say, Rn in this case, some affine constraints, and one interesting constraint, that is that the entries of my decision variable vector will be entry-wise non-negative. Okay, so this is at least one way you can write a linear program, one standard form for linear programming. And the picture is that we have some region here, the non-negative orthant, okay, corresponding to that inequality constraint. And in addition to that region, we have some affine constraints in blue, which kind of slice that region. And the actual feasible region of the problem is this red, the red region in the bottom corner. Okay, and in general, it's not so easy to see in this picture, but in general, it's going to be a polyhedron. So it's going to be something that kind of is defined by a bunch of, these are meant to be straight lines, a bunch of linear inequalities. Okay. All right, so this is what linear programming is. It's optimizing a linear function over a polyhedron. It's specified by very concrete data, a vector specifying the cost, so something specifying the affine constraints, and this orthant constraint. And just one sort of warning I want to make, if you really haven't seen this too much before, something that's very confusing the first time you see it is people say, oh, this is the standard form of linear programming, but then on every other slide where they write a linear program, they write it in a form that looks differently. So I just want to warn you about that, generally, we'll still call it a linear program if there's a mix of linear equality constraints and also linear inequality constraints that look like this. So you can kind of massage things into different forms using standard tricks. So basically, don't worry if you start to see things that don't quite look like this, and I call it a linear program. Trust me, you can rewrite them in this form. Okay, so that's linear programming. What we want to do now is kind of move out of the linear world into something non-linear, and see kind of a generalization of linear programming that still enjoys many of its good properties. Before I do that, I want to remind you of some basic linear algebra facts that are going to be sort of really useful in what we do next. Okay. So the next sort of optimization problem is going to involve things called positive semi-definite matrices. So these are, we say a symmetric matrix is positive semi-definite if one of a gazillion equivalent conditions hold, but sort of a couple that we're going to be thinking about in these talks. The first one is, we'll say a symmetric matrix is positive semi-definite if I take any vector, say if this is n by n in Rn, and I form this quadratic expression, u transpose xu. If that quadratic expression is non-negative for any u, okay, then my matrix is positive semi-definite. Okay. Another equivalent definition is my matrix is positive semi-definite if and only if it has a kind of square root. Okay, so I can factorize it as some matrix transpose times itself. Another one that we won't be paying too much attention to, but I put it here because it's sometimes quite concrete, is that, well, a symmetric matrix, if you recall, has real eigenvalues, and a symmetric matrix is positive semi-definite if all of those eigenvalues are non-negative. Okay, that's this third condition. And to get you primed to think about what's coming later, you can, via essentially this first bullet, you can associate with any symmetric matrix a quadratic form, a quadratic polynomial. Okay, and the positive semi-definite matrices really correspond to non-negative quadratic forms. Okay, so this is kind of our first taste of thinking about non-negative polynomials, but instead of thinking about them as polynomials, here we typically think about them as symmetric matrices. Okay. All right, so these are PSD matrices. What is semi-definite programming apart from a permutation of the acronym? Well, this is something that looks a lot like a linear program, but we just change it up a bit. So now the decision variable is going to be a symmetric matrix. Okay, I'm still going to have a linear objective function. You can convince yourself, if you haven't seen this before, that trace of two matrices is really just kind of like the dot product of the matrices in some sense. And then my constraints, again, I'll have some affine constraints. So A is just going to be, script A is going to be some linear map. We're not thinking about the details too much. But the other interesting constraint now is that my decision variable matrix X is now going to be one of these positive semi-definite matrices. So I'm going to ask for it to be positive semi-definite. Okay. And so again, like the interesting stuff in this problem is the non-negativity constraint. Everything else is just linear. But that's really kind of what makes all the interesting stuff happen. So just as we had this kind of picture for linear programming, we can have a kind of a picture for semi-definite programming where we have a cone constraint. So that's, this is a picture of the PSD cone for 2x2 PSD matrices. It's very misleading in general, but it's a nice picture for this purpose. We're going to intersect with some affine space coming from those linear equations, and we'll get some feasible region for this problem, and we'll be optimizing linear functions over this feasible region. Just a warning, in general, these feasible regions will not be nice and smooth like in this picture. They'll be convex always, but they could be quite complicated convex sets. All right, and again, there's this game that we're going to mix and match our constraints, and we might not always write things in standard form. So that just be aware. And of course, we can extend this story to have multiple symmetric matrices as the decision variables, asking for them all to be positive if we want to. Again, that's kind of, it's secretly captured by this standard form, but it's not so easy to see if you've never seen it before. Okay. The thing I really want to say about this is that, I didn't say this about linear programs, but linear programs are great because we can solve them. And like humans are really good at solving linear programs now. They are really the workforce of modern operations research. Semi-definite programs are interesting also because to some extent we can solve them. And I don't want to be a whole lecture to talk about the extent to which we can solve semi-definite programs. But I think what I want to say for now is that for small to medium-sized problems, and let me say that means up to maybe 100 by 100 decision variables, we have algorithms that solve these problems to high accuracy in a reasonable amount of time. So this is something you can do on your computer. There's well-developed algorithms that have been around for kind of 20 years, quite reliable. And there's also kind of modeling software that you can use to write your problem in a human understandable form, and then it gets passed to the algorithm to solve and gives you back the solutions. This is, I wouldn't say it's a technology because certainly when it comes to kind of badly conditioned, whatever that means, semi-definite programs, they're hard to solve, or they're not so easy to solve in practice. If you're a sort of complexity theorist, the computational complexity of solving semi-definite programs is still open. It's not quite clear what it is. So there's a bunch of gremlins in the details, but like in practice, it's a reasonable assumption to say that you can solve these problems reasonably well, as long as they're not too big and too difficult. And one of the key things in Georgina's talk is going to be talking about, okay, how do you start to overcome the situation when you are actually trying to solve semi-definite programs that are quite big. Okay, so this is semi-definite programming, and for us, we're going to just assume these are things that we can solve, okay, for better or worse, but that's the first assumption we'll make. So where do we go after semi-definite programming? Right, well, you probably started to see the pattern. We could go to any kind of optimization problem where I have a linear objective function. I've got some kind of affine constraints, and then I have some interesting constraint. Right? And an abstraction that's really beautiful and really powerful is to think about my interesting constraint as being a convex cone. So what is a convex cone? Okay, convex cone is a subset of a vector space that's closed under non-negative scaling and closed under addition. All right, so the non-negative orthant is a convex cone. The positive semi-definite cone is also a convex cone. Another really interesting example is that non-negative polynomials, globally non-negative polynomials, form of a particular number of variables in a particular degree, form a convex cone. If you add up two non-negative polynomials, the sum is non-negative. If you multiply the non-negative polynomial by a non-negative scalar, you again get a non-negative polynomial. Okay. So there are many, many more interesting examples of convex cones, and you're going to see some more of these examples in both Georgina's talk and in Marika's talk. Okay. So sort of be on the lookout for new interesting convex cones later in the week. So what can we say about algorithms? Well, one of the nice things about this abstraction is basically whether or not you have any hope of algorithms depends on whether or not your convex cone has any kind of reasonable description. And so if you have a good description of the cone, and that can mean a thing called a barrier function or a thing called a separation oracle, so some kind of computational access to questions like, given a point, is it in the cone or not? And some more complicated questions, then we can get efficient algorithms for these problems. Okay. But that's really the key thing, is that you need to have a good computational description of your cone to be able to have efficient algorithms. All right. So I just want to say something about the cone of non-negative polynomials, and then we'll move on to the third theme of today's talk. Okay, so the cone of non-negative polynomials in n variables of degree 2d. Okay, so this is a convex cone, as we sort of argued on the previous slide. And it's a convex cone that lives in a pretty big dimensional vector space, unless n and d are quite small. Okay, so it lives in an n plus 2d, choose 2d dimensional real vector space. And I think that the connection I want to make for you is that this crazy optimization over non-negative polynomials problem that I put up, on the second or third slide of this talk is really conic optimization with respect to this cone of non-negative polynomials. Okay, all right. So having said that, we've also seen that optimization over non-negative polynomials, if we could do it, we could solve all kinds of hard problems. We could solve NP-complete problems and so on and so forth. So we shouldn't be able to do this. Okay, so what's the catch? Well, even checking whether a polynomial is globally non-negative turns out to be hard. And so we can't really hope to solve these, directly solve, in most cases, or directly solve conic optimization problems with respect to this cone of non-negative polynomials. What we can hope to do is find tractable approximations of this cone, and in particular, tractable sufficient conditions for global non-negativity, right? And if we can find such tractable sufficient conditions, that will give us a way to systematically approximate these optimization problems over non-negative polynomials with hopefully something a bit simpler. All right. Okay, and that's where we're going next. Okay, so the last kind of section of today's talk is about non-negativity and something else called sums of squares. Okay, and sums of squares is going to be our concrete, more easily checkable sufficient condition for non-negativity. All right, so we start with the question. Here's a polynomial of degree 4 in 2 variables, not that complicated, but still, is this a globally non-negative polynomial? So it's not so obvious. I mean, there's some coefficients, positive, negative, although the coefficients don't help you too much. There's odd and even degree terms. So it's kind of not easy to see by eyeballing this, whether it's globally non-negative. You could, of course, plot it, but, maybe the region of the thing you plot doesn't include the smallest value. So it's also not so clear from a plot unless you're careful and you think more. Okay, but if I write it in this way, and I'll leave you at home later to check that this is an identity, then it should be clear that this is a globally non-negative polynomial. All right. So why is that? Well, I've written this polynomial as a sum of squares of other polynomials. Okay, and because when you square a real number, you get a non-negative number. Okay, it's clear that whatever I plug in for x and y into the right-hand side will give me a non-negative value. Okay, so this is a sum of squares description of this polynomial. And it's obvious that if you're a sum of squares, we abbreviate this as SOS, S-O-S, then you're non-negative. Okay, and so what's the definition? We'll say that a polynomial P is a sum of squares if there are some other polynomials qi, such that p is a sum of squares of the qi's. Okay, so easiest definition ever. All right, and so again, if you're a sum of squares, then you're obviously non-negative. There's some natural questions that arise, okay, and have been around for a long, long time, as we'll see, is, well, okay, that's nice. Is it actually true that all non-negative polynomials are sums of squares? Okay, so is this sum of squares condition actually equivalent to being non-negative? Okay, regardless of the answer to that question, is this sum of squares sort of condition actually helpful, right? In the sense that, can we actually, if something's a sum of squares, can we find a sum of squares description of it? And, you know, how do we work with this sum of squares type idea computationally? So first things first, when, and by when I mean for which numbers of variables and which degrees are non-negative polynomials always sums of squares? Okay, so there's really three cases. Okay. So a non-negative polynomial is a sum of squares if the polynomial has degree 2. All right, and that's very close to what we just said about PSD matrices. Okay, so somehow our two descriptions of PSD matrices and U transpose L transpose LU so are really saying, these two equivalent descriptions are really saying that non-negativity and sums of squares coincide. Okay, so the square root description gives you a sum of squares description of this non-negative quadratic. Okay, so this is kind of what's going on in the degree 2 case. It's also true for univariate polynomials. Okay, so somehow for univariate polynomials, if you're non-negative, then you're a sum of squares. Okay, so this is a little bit less obvious, but you can prove this from the fundamental theorem of algebra. Okay. The really interesting kind of exceptional case is that if you have a polynomial in 2 variables of degree 4, and it's non-negative, then it's a sum of squares. It's kind of crazy, and so Hilbert figured this out. Hilbert did more than this. He also showed through a non-constructive argument that in all the other cases, there are non-negative polynomials that are not sums of squares. Okay, so sum of squares only captures non-negativity in these very exceptional situations, kind of low degree, low number of variables. But it wasn't until the 60s until people really found explicit examples, and these two are some of the most famous explicit examples. So this is in 2 variables of degree 6, which is what happens when you take this critical case and bump the degree up. Okay, the second example is in 3 variables of degree 4. That's what happens when you take this critical case and bump the number of variables up. So in both of those situations, these are minimal situations. There are concrete counterexamples that show that non-negative polynomials are not always sums of squares. Okay, I think the other thing I haven't said is that, of course, in order for a polynomial to be non-negative, it has to have even degrees. So you're going to see me write degree 2D all over the place. Okay, and you can convince yourself that if something has odd degree, it has no hope of being globally non-negative. All right, so that's the first question. That's when a non-negativity equals a sum of squares. And it's like sometimes, but not very much, is the shortest answer, although that's perhaps obscuring the truth. The other question is, like, how can we actually recognize sum of squares? Can we work with this condition concretely? All right, so let's go to another example. This is a univariate example, but it shows the idea pretty easily. So this is a polynomial, and it turns out to be a sum of squares. Okay, and we can rewrite this sum of squares description in the following way. Okay, so think about the first square here, x squared plus 1. What I'm going to do is take a vector of monomials. Okay, and if you think about multiplying these two matrices together, okay, the first column times this is going to give you x squared plus 1. This vector of monomials times the second column is going to give you 2x squared minus x minus 1. Right, and the same on the other side. And so if you multiplied this out, you would get that sum of squares description. Now, if I multiplied out just the matrix in the middle, this should be a positive semi-definite matrix. Why? Because it's got a kind of square root as L transpose times L. All right, so, and you can imagine generalizing this argument. You take a sum of squares, you write all the monomials in all the variables up to half the degree on one side and on the other side. Okay, you write the coefficients inside the sum of squares as columns and then as rows. Okay, and then you multiply out the inside matrix, and we'll get some description of a sum of squares in terms of a PSD matrix in the middle here. All right, so hopefully it's clear that this idea is not special about univariate polynomials. It's just whenever you're a sum of squares, you could do this kind of thing. And also, whenever conversely, if you had a vector of monomials, and I'll call that MD of X, all right, and you had a PSD matrix, which I can factorize, all right, and I expand things out, I will get a sum of squares. All right, so if I'm a sum of squares, I can write things of the form monomial vector transpose times positive semi-definite matrix times monomial vector. And conversely, if I have a description like that, I can extract a sum of squares decomposition. All right. Okay, and that's what it says here. If in general, if you start with a polynomial in degree 2D, what you need to do, you need to consider monomials up to degree D in here. Okay, and then your polynomial is a sum of squares if and only if you can write an identity with your polynomial on one side and this kind of weird expression on the other side where the matrix in the middle is positive semi-definite. Okay. All right, so that's kind of building off this example. All right, so suppose I give you a polynomial P and I want to try to decide whether or not it's a sum of squares. So I don't tell you if it's a sum of squares. I want us to try to figure this out. So how could we do this? All right, well, we know that if it's a sum of squares, it must have a description of this form where this matrix in the middle, that we often call a Gram matrix, is positive semi-definite. All right, and I want this identity to hold. So one thing I could do is that I could equate coefficients on both sides to set up some equations that relate the coefficients here, well, with the minus sign, to the entries of the matrix. Right, and if you do this, you get a bunch of linear or affine constraints on Q. All right, some of them are not very interesting in this case, but there's at least one interesting one on the end. Okay, that means that there's many different matrices Q, symmetric matrices Q, that when you try to write down this identity, will give you that polynomial. Not just one, there's many choices. And to decide if P is a sum of squares, we need to decide whether there exists a positive semi-definite matrix, okay, that satisfies these affine equations in Q. All right, so if there is, this thing's a sum of squares. If there isn't, this thing is not a sum of squares. Okay, so searching for the sum of squares decomposition of a polynomial is a semi-definite programming feasibility problem. Okay, so it's asking about whether the feasible region, whether a semi-definite program defined by a PSD constraint and some affine constraints is feasible or not. Okay, and we can do that also using algorithms for semi-definite programming. All right. So the last kind of connection I want to make between sums of squares and semi-definite programming that we're going to use over and over again without thinking about it in the future is the connection between the semi-definite programming and sums of squares. So before, we just talked about a single polynomial and asking about whether a single polynomial is a sum of squares. But it's going to be very beneficial for us to think about the whole, it turns out, convex cone of sums of squares. So we're going to leave you to think about why polynomials that are sums of squares that are in n variables of degree 2D, why they form a convex cone. Okay, but they do. And it turns out, for example, we're going to call that sigma n comma 2D throughout the talk. So sigma for S for sum of squares. And in our example on the previous slide, the sum of squares cone is going to be the collection of polynomials you get. Okay, the sum of squares cone in one variable of degree 4. It's going to be the collection of polynomials you get by starting with a positive semi-definite matrix that's 3 by 3, and then writing down, what the coefficients would be in this identity. Okay, so if you take any positive semi-definite matrix and you push it through those linear equations, these are the coefficients you would get out, right? And so this forms for us a nice convex cone. It's in fact the image of the positive semi-definite cone under a linear map, right? And this observation means that in general, this is a convex cone, so I could write conic programming problems with respect to the sum of squares cone, right? I can put any convex cone in there. But what's nice is that conic programming problems with respect to the sum of squares cone can always be rewritten as semi-definite programs. So a lot of the time later, particularly in tomorrow's lecture, we're going to see optimization problems with constraints that a polynomial is a sum of squares. You should automatically recompile that in your mind just to say, and so we can rewrite that as a semi-definite program and solve it using standard algorithms for semi-definite programming. Okay. All right, so the cone of sums of squares is some kind of thing that can be rewritten in terms of SDPs. Importantly, it's an inner approximation to the cone of non-negative polynomials, all right? Because remember, being a sum of squares is a sufficient condition for being non-negative. So everybody whose sum of squares is non-negative, but in general, not conversely. All right. So I want to the last non-trivial thing I want to do today is kind of a teaser for tomorrow's lecture. Okay, it's like, I don't know, it's like trying to get you to binge watch the lectures, except we're not binge running them. Okay, so I just want to give you a hint of how we put these pieces together to do something interesting. Right, and this is a hint, and we're going to see much more the full toolkit tomorrow. Okay, but how do we use this sum of squares idea to tackle unconstrained polynomial optimization problems? Okay, and I'm going to start with some polynomial that's non-negative. In fact, this is one of our examples of a polynomial that's non-negative, but not a sum of squares. Okay, so it turns out that the minimum value this polynomial can take over R3 is 0. For example, if you plug in the origin, you'll get 0. And remember that we think about reformulating this unconstrained polynomial optimization as maximizing a global lower bound on our polynomial. All right, so maximizing a constant polynomial gamma such that P minus gamma is, so P34 means a globally non-negative polynomial in 3 variables of degree 4. So the optimal value of that problem is 0. Okay, and so what's the basic idea? The basic idea is to replace non-negativity with sums of squares. Okay, so replace this cone with our sum of squares cone. If we do this, this will give us a lower bound. So why is that? Because the sum of squares cone is smaller, all right? So this will be a more restrictive constraint, all right? And so with a more restrictive constraint, the maximum will get smaller because we've reduced the size of the feasible region, okay? And so what happens if you compute this, and we're not going to compute it right now, but one can compute this by translating this into a semi-definite program and running a semi-definite programming solver, is that, the basic sum of squares relaxation that looks like this, it can't compute the exact minimum, and it shouldn't be able to because this polynomial is not a sum of squares, okay? But it can compute that the global minimum is at least negative 0.138. Okay, so you can do something non-trivial with these tools. All right, so what have we done today? We've seen that polynomial optimization problems are expressive, okay? We're focusing in these lectures on giving global lower bounds on minimization problems and ones that we can certify, okay? So to try to complement the arsenal of tools we have for producing upper bounds on minimization problems by improvement, okay? There's a strong connection between polynomial optimization problems and conic convex optimization problems where the decision variables are polynomials, but we constrain them to be non-negative polynomials. The problem is that those problems are too hard to solve. Okay, so what we're looking for is some sufficient condition for non-negativity that allows us to actually get something computationally tractable. Sufficient condition is very natural, and a starting point is that a sum of squares of polynomials is always non-negative. Okay. And so the big idea is that we're going to approximate optimization problems over non-negative polynomials with optimization problems over sums of squares. And we can reformulate those as instances of semi-definite programs. And this gives us, at least so far, some kind of certifiable lower bounds on unconstrained polynomial optimization problems. So we've done, something. What's coming up next, particularly tomorrow? So what we're going to do is look at, how do we incorporate constraints into this story? How do we improve the lower bounds, techniques for getting lower bounds? And like a little bit of what's the theory behind this approach? So what kind of guarantees do we get on how good the bounds can be? At least at least as we allow our convex optimization problems to get bigger and bigger. Right, so that's going to be the focus next time is really on taking the ingredients that we built today and making an actual toolkit that you can go and use to tackle problems. Okay, thanks.
Thanks very much, James. I guess we can field some questions, James, just briefly.
Yeah, I can hang around for a while. Also, if people need to
That's
go.
right. We've gone a little bit over time, but if people want to stay back and ask questions, please do. And I'd like to thank James for a really lovely talk. That was a great introduction and very enlightening. So thanks a lot, James. Do we have any questions? I have a question, James.
Yeah.
I'm actually interested in to what degree continuous optimization problems can model, combinatorial optimization problems. And so, when you do the binary things, you put a polynomial down that has a root that's a binary variable. Clearly you could interpolate a finite number of integral points with a polynomial, right?
Yes, a finite number. Yes,
a finite number, and if you've got a bounded region, you could definitely have the polynomial constraints that would interpolate.
Yeah, although I think it gets like quite bad in the sense that
so it's not a really efficient way. So I guess my question was, to what degree do these problems, manage to model, an integer programming problem on a bounded set, I suppose, Yeah,
I think so. I mean, I think it's hard to say in general anything about this kind of thing. I would say in practice, the problems for which there's been some success I think in this viewpoint have really been binary problems or problems of very small state spaces for exactly the kind of reasons that you say, like to once you start having a large potentially, I mean, the other thing is in integer programming, you often don't know, it's not that easy to tell a priori how big the integers are going to be.
Well, true. This is true, but sometimes you can, that's the thing about binary problems, you do know.
Yeah.
Absolutely. But many hard integer programming problems, you're going to get lower bounds anyhow, which is all you're doing.
Right. That's right. And again, I think this idea of lower bounds is very much ingrained in the integer programming world, right? And this is how branch and bound and so on works. So that's right. So it's a different technique. I don't know how. I mean, certainly people have studied using these techniques in certain problems. But I think often the game, and it's hard to say everything, but is that since this story is so, these polynomial optimization problems are so expressive. I mean, you obviously can't. There's no silver bullets. And the game is to find, okay, which problem has the right structure that somehow these techniques are actually useful on, and to then find that and exploit that. Right? I think it's quite challenging to find this.
Okay, well, just one more question along these lines is that, as you mentioned, branch and bound. Well, all you need is a bounding function, and a bounding function will be able to plug into branch and bound. You can get an exact solution. So have people use this bounding process, found a suitable, class where you can, bound reasonably tightly, and then branch and bound does the rest of the job?
I mean, I think the answer to that is definitely yes, that people have done branch and bound schemes with things that could be interpreted as polynomial-like lower bounds for the problem. But I don't think, I would say that's maybe isolated situations. I don't think that's a systematic and widely used tool. I think the other thing to say is that that a big difference is that linear programming. We can really solve linear programs, right? I mean, you could solve huge linear programs. It's incredible technology. Whereas SDPs are not that at this point. I mean, it's much harder to solve them, and there's real scalability issues, and that's really what Georgina is going to sort of give us a taste of on Thursday. And so it's quite there's all sorts of conditioning issues and other things with SDPs. So I think that's probably one of the reasons why, in practice, kind of reaching for things based on linear inequalities it turns out to be quite a bit more powerful for those problems.
Sure, yeah. I don't mind keep on hogging the questions for the time. I'll have one
Well,
more.
we can see if anyone else is.
Is there anybody else would like to ask the question before I ask the last one? Okay.
Go ahead.
Go ahead, Ryan. You
Sorry,
go ahead.
thank you.
Yeah.
Thank you for the talk, first of all. Can I ask a simple question I think you mentioned that for the sum of square, even though a polynomial is sum of squared, so its decomposition is not unique, if I'm right? So,
well, generally, yeah.
Yeah, so is there a way to, what is the optimal size in terms of small links to decompose it? And could you update me on the state of R? And is there a constructive way to find it as well?
So I don't know the state of the art for that question. So this is a whole kind of question people study of, I think it's called the Pythagoras number. I think
Yes.
is the quantity, and it's related to, I think, as you probably know, a kind of notion of rank with respect to a variety. So so I don't know the state of the art on the bounds on that quantity for different degrees and number of variables. Of course, for those who perhaps are new to this, one classical result is that for univariate polynomials, two squares is enough in your sum of squares decomposition. That's something that you can, when you go and prove that univariate non-negative polynomials are the sum of squares, usually kind of comes out of the proof. But yeah, I don't know what the state of the art results are right now. Okay, your question is, can you constructively bound this rank? Yeah, and so again, I don't know. I think you can. There are generic tools for sort of, again, for trying to bound ranks, more exotic ranks than the standard rank. And the context in which I know it is people trying to bound the non-negative rank of matrices, which is a little bit different, but there are some kind of somewhat more general techniques people developed in that context that may be applicable for these ranks with respect to a variety. Yeah.
I see. But thanks for the information.
Yeah.
All right, thank you. That's all for me. Thank you.
Are there other questions from the audience?
Particularly like super basic questions about things that were not clear are very welcome, right? Or things that maybe are not super basic questions, but that feel like
I'll ask my other question, James. When you're generating these lower bounds, by having these relaxations, can you get a kind of a gap? Is there an upper bound that you can generate somehow?
So sometimes, that's kind of a big question. I think I'll talk about some different instances of this where people do understand something about the quality of these approximations, probably on Wednesday. That's, of course, a very natural question. And in general, it's quite challenging to understand the quality of approximations. But for specific problems, and one of the poster child problems is, for example, this max cut problem that we started with. This is a situation where we do understand at least kind of the simplest relaxation. We understand something about it's the gap in this lower bound.
Right.
But this, like, understanding that more generally is connected to difficult open problems in complexity theory and so on. So it gets tricky quickly.
Yeah.
There are some special nice situations where people understand things. Yeah.
Okay. Are there any other questions? Please put your questions in the chat if you wish to, or just unmute yourself and ask James a question. Okay. If there's no other questions for James today, then I'd like to thank James, and we'll reconvene again tomorrow at 5 o'clock and for the next session. So thank you very much, James, and we'll say anon and meet you again tomorrow.
Sounds good. See you all tomorrow.
Okay.
Thank you very much.